want to real quick discuss what I would like to term the two I/O fallacies, all right? The first one is the IOPS fallacy, and then the next one is the I/O response time fallacy. So let's talk about the IOPS fallacy first. First, what is the myth? The myth is that I have more than enough IOPS to handle the workload. Maybe I've got an all-flash SAN. I've got 600,000 IOPS on it, which is actually a real use case that we had. It was very, very interesting on this one particular use case that I went through. They had a all-flash pure SAN, 600,000 IOPS, and this was a server POC we did. They only had 11 physical servers attached to it because the workloads were so heavy and they were really missing their SLAs. Their data warehouse server, we were able to shave the overnight job in half, from 7 hours to 3.5, and we were able to shave about 15 minutes off their SQL workload, which got them under their SLA. So it's kind of an interesting thing to look at. So when we look at the reality of this, workloads are processing 30 to 40% slower than they need to be due to, and you're going to hear this theme a couple of times, the nature or the way the I/O is structured when it gets issued from Windows. So Windows is creating a data pattern of small, split, and random I/Os. That's generated directly by Windows. Now, a point here is that sequential I/O always outperforms random I/O on any hardware that you want to run tests on. So that's going to be very interesting. So when we look at that and we want to look at what's the truth of the situation, only a small percentage of the total I/O capacity is being used at any one time, right? For example, if I walk into a crowded room, and let's say the room has 20-foot ceilings, and this room is packed. There's shoulder to shoulder. And someone comes in and says, okay, your mission, should you choose to accept it, is to walk from this side of the room to that side of the room and not touch anybody else. This message will self-destruct in 5 seconds, right? I'm not going to be able to pull that off, even though I've got 15 feet of clear airspace above me, because I have to use the working space down here where everyone's standing in that 5 to 6 feet of space. So that's a really good analogy for when we have over-provisioned hardware. We're looking at, hey, I've got these huge IOPS ratings. It doesn't really matter. What we want to look at is the 3% of the IOPS you are using. We can make that 3% go 30 to 40% faster. The rest of it's just a distraction. So that's what we really want to focus our attention on. And what happens is with those high IOPS ratings and all that headroom is we get this false sense of security because of all of that rating. And what we're really losing is the way the Windows is designed and sends data out, it really is sapping 30 to 40% of the throughput potential out of that hardware, and we can give that back to you. So that's the first I/O fallacy. So the other thing that we want to look at then is what is that second I/O fallacy, and that is the I/O response time fallacy. Okay, now this one's really interesting. We can really get misled by I/O response time. We like to look at, let's take a look at the myth here. We like to look at the sub-millisecond response times on individual I/Os, and that also gives us a false sense of security because we think that faster I/O response time is better. That is not always the case, right? So let's look at the reality. One individual smaller I/O transfers faster than one individual larger I/O. So if you had like a 4K I/O versus a 64K I/O and you time them, 64K is going to take longer. The other thing this doesn't factor into play is that it doesn't take into account the configuration of the I/O. You have split I/O versus contiguous I/O. You also have random I/O versus sequential I/O. And all three of these factors play in significantly. So that's what we really want to look at. And the truth of the matter is that the individual response time of each I/O is really over prioritized when we're looking and analyzing what our throughput is. It's important, yes, and having flash is a wonderful thing, but it has been over prioritized because of this missing of what's the nature of the I/O. And the overall throughput is always going to be slower when data is transferred with small split random I/O, and it's always going to be faster when it's transferred with contiguous larger sequential I/O. And we're going to get into here shortly exactly how velocity transforms I/O at the source within the Windows operating system so that we get the contiguous larger sequential I/O that gives you 30 to 40% faster throughput. We're also going to talk about how this is optimized, this optimization work is done while lowering resource consumption on a system, lowering CPU utilization, things like that. And that's going to be coming up in these use cases that we're going to jump into right now. So Howard,